A very good evening to all of you. So today we are going to start the synchronous motor, and we'll be taking some numericals on the synchronous motor. So to start with, synchronous motors are broadly classified into two types depending upon the rotor construction. The first one is the cylindrical rotor wound field motor, and second one is the salient pole rotor. So now in this case we are going to discuss the cylindrical rotor. As you know that the synchronous motor is also a motor which is going to convert the electrical energy into the mechanical energy. So we can say that we are having voltage and the current as the input variables, and torque and speed as the output variables. So when we talk about the synchronous motor, we generally take a three-phase synchronous motor. So in that three-phase synchronous motor, the input power will be PV. P input will be equal to 3 into V, I3 into V into Is into cos phi. So here what we can say that the V is the per phase voltage, Is is again a per phase current, and cos phi is the power factor angle. It is the angle between V and the Is. So generally, we neglect the losses. As you know that the synchronous motor will be having the stator and the rotor, so there will be resistance and the reactance. So in that case, you will be having the stator losses. But generally, we neglect these losses, and when we neglect these losses, it means that the input power will be equals to the mechanical power, and mechanical power will be equals to 3 into V into Is into cos phi. So what we are doing, we are just impressing a voltage, and we are getting speed as the output, or you can say the torque as the output. The first torque will come, and then the mechanical speed will come. So if you want to represent that thing in the form of equivalent circuit, so that can be represented by the induced EMF. As you know that this E is a function of the speed. So this is the electrical equivalent of the mechanical speed. So we cannot represent the entire thing, that is stator and the rotor, in the form of equivalent circuit. So we will have to take the reflection of it. So whatever the changes will be there in the speed, that will get reflected in the form of the induced EMF. So now you are having this voltage induced EMF, and as you have already neglect the stator losses, it means that the resistance will not be there. So simple Ix, as for simple XL, that is a synchronous reactance. You have neglected the synchronous resistance, so you are having a simple circuit. Now this circuit is of the per phase. We have not taken three phases because we have assumed that the three phases are the balanced one, and when we are saying that the three phases are balanced, it means that the you can have the per phase equivalent circuit. So so now if you apply a KVL in this circuit, this is what is going to get. Now you can see here V is the vector quantity, so it has got the magnitude as well as the angle. Generally we take the voltage as the reference, that is the input voltage as the reference, and with respect to this V, we have to plot all the other variables, that is electrical variables. So generally we plot the current with respect to V and E with respect to B. So the angle between V and the I, as I have already told, is a power factor angle, and the angle between V and E is the delta angle. Now you can see here the first voltage has appeared, then after that the speed, and because of the speed you are getting the reflection of the induced EMF. So obviously this will be lagging with respect to V. So we have taken here minus a delta, because this is V angle 0, this is minus delta, and here you will be having the power factor angle, that is minus 5. It might be any type of power factor. This is the only motor which can operate in different types of power factor. You can have a unity power factor operation with a synchronous motor. You can have the lagging power factor operation with a synchronous motor, you can have a leading power factor operation with a synchronous motor. So what you have to do, that I'm going to tell you. So now if you apply a KVL, simple KVL you will have to apply. There's a current is going to flow, so there will be plus and minus. So if you are going to trace that thing, so it will be this will be the that is is will be equals to the angle of 0. And normally we take the reactance as the as a reactive part. Resistance is a real part. uh, I have told this in many lessons. And reactance is the reactive part, so we have taken that as J into Xs. Or else you can say that this J means what? That is angle pi by 2. If you have calculator, then please write J and convert it into the polar form, and you will be getting this as angle pi by 2. So if you are going to simplify this, so this one will be minus pi by 2, and here minus delta minus pi by 2. So minus will be common, and inside bracket you will be having a pi by 2 plus delta. Hmm. So now plus we want only the horizontal part. So we have taken the cos of the entire equation. So that will be is into cos y. That is vs into cos pi by 2. This will be 0. Cos 90 will be equals to 0. And here, what you will be getting, you will be getting e upon x's into sine of delta. So this is the is into cos phi. So now you just have to replace this is cos phi by e upon x's into sine of delta. I think we have done this part in the facts. So the this is the mechanical power which you will be getting. And so now, as you know that the synchronous motor is rotating at the synchronous speed, it means that the magnetic field and the rotor will be having the same speed. Rotor will also rotate at a synchronous speed, and magnetic field is also rotating at a synchronous speed. So in that case, how you are going to find? Now you know that ns will be equals to what? 120 MIP. That will be in the revolutions per minute. But if you want in revolutions per second, then you will have to divide that entire equation by 16. So 120 MIP divided by 16. So what you are going to get? I think it will be 2 a by p. Okay, and we want the angular speed. What is the angular speed? That is 2 pi f. 2 pi, 2 pi, 2 pi into what we can write? 2 pi n. Omega will be equals to 2 pi n. So 2 pi into 2 f by p. So you'll be getting this as the rotating magnetic field. And similarly, now when you having the mechanical power, you can simply calculate the torque. So P will be equals to omega into T. So we take T will be equals to P upon omega, and this will be your speed. So now this is for the motoring operation. Everything will be positive. You are taking V as a reference. When you are taking V as a reference, it means that you are sending the power from the stator side to the rotor side. But if you want a breaking of it, normally there are two important operations which we have dealt with. The first one is the forward motoring operation, and second one is the regenerative braking operation. So in that case, what you will have to do? You will have to make torque negative. Only in that case, your power will flow in the negative direction. Is it not? So in that case, how you are going to do? So we will have to make this delta as negative. Now what? Now this delta, if you can see here, V is right. V is leading with respect to E. So in this case, you are having the motoring operation. So, but if you want the braking operation, then you will have to shift this E ahead with respect to your that is the input voltage. Only in that case you will have the braking operation. Speed will be the same only. So this is how you can have the braking and the motoring operation. I have already told you that the synchronous motor can be operated in three different operations. The first one is the lagging power factor, the unity power factor, and the leading power factor. Now how? So when the excitation EMF is, you can see here this E is smaller as compared to V. First, we'll have to plot all three electrical variables. Now you know that when you will have to plot the electrical variables in the xy plane, so first you take V as the reference. Now with respect to V, you will have to plot the current. So current will be lagging, obviously lagging power factor. So the angle between V and IS, that will be phi, and the angle between V and E, that will be delta. But when your synchronous motor is operating at a lagging power factor, E is less than V. So you can see here. So you can see here we are having the equivalent circuit. So V will be equals to what? Is into X, Xs plus E. It means that it means that first, you will have to plot V, then you take E smaller as compared to V, then you will have to join IS into XS, then you just extend this IS extend in the reverse direction. So what you are going to get, I will be perpendicular, because you know the current is always perpendicular with respect to IS XS draw, right? So there are three important steps that you will have to understand. First step will be to plot the V as the input voltage, and that will be the reference voltage. Now with respect to V, you have to plot the variables. So what we will do, we will keep field excitation small. Now in this case, we'll have kept field excitation small. Now you can see here E. Now after plotting E, then what is the next step? That is reactive drop. So V will be equals to, from this equivalent circuit, V will be equals to Ix XS plus E. It means that the addition of E plus Is into XS will be your V. Now you can see, you will have to keep one thing in mind, that the current is always perpendicular with respect to Is into XS drop. So in this case, if it is perpendicular, it means what? The V and Is will be in the unity power factor version. Now you can see here, first we have plotted V, then E have plotted, right? And after that, is into xs. Again, you will have to extend this is axis in the forward direction. Only then you can have current perpendicular with respect to the is into xs reactive drop. So in this way, you can have the variation in the power factor by just varying the field excitation. Now, what is the field excitation? Because in the rotor, you will be having the field winding. So the supply to the field winding can be varied, and accordingly the power factor angle can be varied, and your synchronous motor is going to operate in three different power factors. Okay, so now we'll be taking the numerical. So now in this numerical, the synchronous motor is there. That is 500 kilowatt, three phase, 3.3 kilovolt. Voltage is also there. Now this is the line voltage, and this synchronous motor is operating at lagging power factor. So when I say lagging power factor means what? That the field excitation is small. Just now we have seen here. When you want the lagging power factor, it means that you will have to make your excitation small as compared to the V, because you can see here when E is small, so after that from the tip of E you will have to plot Is into Xs, and one thing you will have to keep in mind, that current is always perpendicular with respect to Is into X. So it means that the excitation is small, fine. But we'll be dealing with the per phase equivalent circuit. Now you can see here Xs will be 15 ohm, Rs will be equal to 0 ohm. So what is expected, what we will have to calculate first? The voltage is there, voltage is given, current you will have to calculate. So whenever you will have to calculate the current, that time you will have to take P will be equal to 3 into V into I into cos phi. Now in this case mechanical power is there, and we have already assumed that the stator loss is small, or you can say, because in this case Rs will be equal to 0. Fine, when you say Rs will be equal to 0, the copper loss and the core loss is always negligible. So in that case, you can take this as the input power. So now this is the three-phase power. It means that that will be, either you can have the 3 into V into I into cos phi, or you can write root 3 into VL into IL into cos phi. It depends upon the you. Now, what is the synchronous speed? Here you will have to calculate in the radians per second. So first to calculate in revolutions per minute, that is 128 by P, or else you can calculate in the revolutions per second. Now, what will be the speed in the revolutions per second? It will be simple 2 into f by p. That is 2 into f. F means frequency 15. 2 into 15 upon 4. Simple. And you have to calculate by into 2 pi. So that will be in the radians per second, because your rotor is rotating at a synchronous speed only. This is not the induction motor. The rotor is not rotating at a different speed other than the synchronous speed. Fine. So this you will have to keep in mind. So what I told you that you will have to calculate the rated current, because we have not gone through this what we want now. First, we try to find the rated current, rated input current, which I can take, because my this is a nameplate, and I just want to calculate the rated current. Everything is given. I want to calculate the rated current. So just now I told you that when you want to calculate the current, then you will have to apply this equation. So this equation is applied. You will see all the quantities are vector only. These are not the scalar quantities. Fine. So so now you put all the things, and now the is will be equal to 109.3 ampere. So if you want to write in the vector thing, now this voltage will be taken as a reference. So current is lagging with respect to the phi. So that will be what? Minus cos inverse, because this is a lagging power factor, and zero point 0.8 is given. So that will be cos inverse will be what? Minus 36.86. 36.86. This will be the thing. So now here current is calculated. Now suppose if you want to calculate the excitation, so from where you will calculate? Excitation will be calculated from the per phase equivalent circuit. So in that case, V will be equal to E plus I into Xs. Fine. Yes, I have written the scalar form, but you have to write in the vector form. So if you want to find E, it means V minus Is into J into Ix, as all are vectors. Fine. Voltages angle is 0. Now here 1905.2, it means that per phase voltage I have taken. Per phase voltage, don't write here three phase, that is you can say line voltage, because we have taken into account the per phase equivalent circuit, as we have assumed that the three phases of the synchronous motor are balanced. So all the equivalent circuits are same only, otherwise you will have to draw all the equivalent circuits, and then you will have to calculate the excitation for all the equivalent circuit there. Fine. So for simplicity we have done this. Now the current just now calculated along with the angle. So this is the thing. E will be equals to, so now this you have obtained. So before starting with the problem, so you have to calculate the current and the excitation. This is the thing which you have to calculate. And when you have to calculate the current, it means that the power equation, and for excitation, equivalent circuit equation. Now, what is asked that the armature current and power factor at half the rated torque and rated field current. Now you can see here field current is not changed. So I told you that the field current means what? The rotor will be having the field winding, and you will have to apply the excitation. So when whatever excitation will be there, so accordingly the field current is going to pass through the rotor winding. So E will be depending upon the field current. So in this case, excitation has not changed, right? Because rated field current is there, but the torque will be half. So torque will be half means the input current will be half. So that's why you will have to calculate the armature current. This is not a scalar form or proportional form. That previously it was 100, so now it will be 500. It will be some different value. So E is same. Now what you have to calculate? Now suppose if you want to calculate the delta, fine. Because in this case, I think you will have to calculate the delta. Why we have to calculate a delta? Because you can see that the torque has reduced. So when the torque has reduced, it means what? The speed has reduced. And when the speed has reduced, it means that the angle between B and E, is the delta, is going to increase. Fine. So this you will have to keep in mind, that when the torque is reduced, it means that it will be having impact over the power angle, or you can say delta. So that's why I have to calculate a delta. So how to calculate a delta? In this case, so delta will be calculated by simple that equation. So in which equation we are having a delta? I think it will be 3 into v into upon x sine delta. Fine. Delta, I think it is, yeah. So the PM rated torque is, because torque is also half. So sorry, that power is also half. So we have taken this power, and this is 3 into V. Right? Obviously 3 is there, so that is the per phase voltage, and excitation has not changed because the rated field current is there. To calculate sine delta, so after calculating this delta, you can easily calculate using this equation. Fine, because V angle 0. Now you can see here, excitation has not changed, only the delta has changed, and accordingly you will be having this is, and you can calculate the power factor. So now in the second part, what is asked, that is field current to get unity power factor at the rated torque. Now you can see here, torque is a rated one. Torque is a rated one. It means that when the torque is rated one, that means the power will be 500 kilowatt. 500 kilowatt. Only thing, unity power factor. Unity power factor means what? Cos phi will be equals to 1. Unity power factor will be equals to what? Cos phi will be equals to 1. So simple. When you have to calculate, now in this case, V and I will be in same phase. V and I will be in same phase. So V angle 0 and I angle 0. Fine. So you can see here, simple. 3 PM will be equal to 3 into Bs into cos phi. Cos phi is 0. Cos phi is 1. Is is simply calculated. Now again, you will have to calculate this excitation. Again, you will have to calculate this excitation, because you can see here, unity power factor, excitation is equals to V. Fine. Excitation is equals to V. So in this case, E will be equals to simple that formula, V minus J into Ix. So why every time we will have to calculate? Because you can see the previous problem is same, but in this case you can see power factor is unity, means improved one, that is E will be improved one. So that's why we have calculated E, and as you know that it is proportional. So what we can say, uh, what we can say, for 10 ampere, what is the excitation? For 10 ampere, excitation is 1630. Fine. This is a simple ratio and proportion problem. And for this, how much? So you can simply have the ratio and proportion, and you can calculate this 14.43. So I think the concept is very much clear. The concept is very much clear, and you can simply jump over any problem. But the thing that what you have to keep in mind, that when you have to calculate a delta, that means go for that equation. When you have to calculate the current means that E will be equal to 3 into I, Vi into sine phi. So in this way you can calculate the things. Now here, what is asked? Field current is given. So first field current is given. So accordingly you will have to calculate the excitation, because excitation and field current are proportional. So I think this can be easily solved. If you have a problem, you can always contact me. Thanks a lot for the problem. So we'll meet in the next video.